Hello, my name is Isaac, and welcome to activity number 24, Regularized Logistic Regression. In this activity, I implemented regularized logistic regression to solve a binary classification task, predicting whether a client will default using three features: age, income, and scored credit. Logistic regression models the probability of the possible class with the sigmoid function, and I added an L2 regularization to prevent overfitting by discouraging overly large coefficients. I trained the model with gradient descent, tracked learning using a regularized cost function, and then evaluated performance on a separate test file by reporting accuracy and error rate. Finally, I varied the regularization strength, or lambda, to show its impact on generalization, fully aligning with the assignment objective. Now let's take a look into a practical example of regularized logistic regression in Python. First of all, we want to import three libraries: numpy for numerical values, pandas for reading the CSV, and matplotlib to plot or to see the graph. We're also going to use scipy's xsplit or the sigmoid function. The sigmoid converts any real numbers to a probability between 0 and 1. Now we're going to load the training data and pick columns. We're going to read datos_clientes.csv, select the three numeric features are going to be age, income, and scored credito, and we're also going to target defaulting. Features become a numpy array. The target becomes a column vector for math convenience. Now we normalize features with strain statistics. We compute the mean and standard deviation per feature on the training set only. We use std_safe so that any 0 standard deviation becomes 1 to avoid dividing by 0. And we also standardize. This speeds off convergence and makes the penalty comparable across features. Now we're going to add one column for intercept term. We prepare a column for ones to the feature matrix, so the first parameter is the intercept, and we will not regularize. Now we're going to call the initial parameters. We have theta that starts at zeros, the learning rate that will be 0.01, iterations 300, and the lambda regulations are going to be equal to 1. We can also vary lambda to create different experimentation that we will see later. Now we have to add the regularized cost function with the L2 regularization. We're going to compute cross entropy loss and add. We clip probabilities to avoid log 0 numerical issues. Lower cost means a better fit considering both data and penalty. Now we're going to call the gradient descent with the L2 regularization. At each iteration, we compute the gradient of the regularized loss, the data term m plus the penalty term. We update and we store the cost of each iteration to confirm its decreases. Now we have training the model. We're going to call the descent and get the final theta and the full cost history. We plot the cost to show convergence. As you can see, here are all the necessary functions to plot the cost function and the regularization. Now we have the prediction part. For any matrix, we compute probabilities and threshold at 0.5. As predicted, the class is going to be 0/1. Now we're going to evaluate the model. We're going to read datos_clientes test.csv to normalize it using the training mean/standard deviation. At the intercept, predict and compute accuracy and error rate. This test generalization on unseed data. As you can see, this forms part of the normalized test. These are going to be the predictions for the evaluation, and here we're going to print the lambda, the model accuracy, and the model error. So now we're going to run two tests to do a comparison of how the changing lambda affects. First, I'm going to set lambda regulation to equal to 0, as you can see here, and going to run the script. As you can see, here's the graph for the following lambda is equal to 0. Now we're going to close and see the model of error, lambda equal to 0, model accuracy 90C, and model error equals to 4. Now we're going to test number 2 and going to set lambda regulation to 1. Now we're going to run the script. And this will be our new lambda 1 function. Now we're going to close it. And we have also our lambda regulation to 1, a model accuracy of 96, and a model error of 4%. Conclusion: why the difference happens? When lambda is equal to 0, the model is free to grow large weights to feed training data closely, which can increase variance and hurt test accuracy if there's noise or correlated features. With a moderate lambda 0.1 to 1, the L2 penalty shrinks coefficients, safely smoothing the decision boundary and improving generalization, so test accuracy often improves or stays stable while the model is less sensitive to noise. With a very large lambda, for example equal to 10, the model will be underfit, pushing weights too close to 0 and reducing accuracy. And I will run the following code in MATLAB to show a different example of how the graph will look here in a different programming language. So here's the graph. Here's the cost of iterations, and when lambda is equal to 1, and there's a graph. And here we have the lambda, the model accuracy, and the model error. That's the same as before. To wrap up, regularized logistic regression adds an L2 penalty to the logistic loss, keeping coefficients small, improving generalization. In my two runs using a moderate lambda, can maintain or improve test accuracy versus lambda is equal to 0 by producing a smoother, more stable training curve. This confirms that regularization is effective to control overfitting and meet activity's objective, a reliable model that performs well on unseed data. Thank you for watching, and I'll see you next time.